Okay, so we'll talk about test equipment here tonight. Test and measurement, because not all of this is about test equipment. Some of it is measuring items. So what we're going to do is we're going to start off and we're going to talk about Ohm meters. Then we'll look at component testing. We'll do some oscilloscopes, and we'll look at spectrum analyzers, and we'll look at solutions for test equipment from the PC world, and I mean personal computers. But there's really something that we need to talk about first before we get into test and measurement equipment, and that is this. And this is real critical. I got a question to ask you. How many of you have been across 120 volts VAC? Okay, I was expecting just a couple, but wow, okay. So,
how many want to do it again?
Yeah, how did that feel? How did that feel?
How did that work out for you?
How'd that work out? Yeah, I was probably 11 or 12, and I was washing my hands before supper, and I had finished washing my hands, and I dried them off, and I had my hand up on the cold water faucet, and I reached up to turn off the light, and I missed the switch, and instead hit the fixture. Next thing I knew, I was across the room and on the floor.
Wow.
Okay.
But his hands were dry now.
The hands were dry, and I was wondering what had happened. So that was a full path. That was a full path. I had grabbed the light and it was like there. So I probably didn't even feel that. But I did feel it, believe me. So, and that kind of stuff earns you a healthy respect for AC and voltage in general. Now, when I was a young kid, and we'll talk about this later, my dad had a little side hustle where we would buy old TVs at swap meets and auctions, and then repair them and then sell them for a little profit. So he would do everything that he wouldn't trust me to do, like he'd reach in and grab the anode off of the picture tube, you know, and then take that and touch it to the ground, and it would go bang, okay? And that teaches you respect, but when you get across 120 volts of VAC, that's a learning experience. So I went out there and I looked for stuff about safety in testing, particularly with ham radio, and I can't really say I found a lot. I found a lot of antenna safety, but I didn't find a lot about ham radio safety and testing equipment. So I did search several sites, so I came up with some rules, okay? The first one is you got to be aware of what you're trying to measure. Are you looking for some 5 volts? Or are you looking for 7 kilovolts on an anode for, say, a scope or a picture tube or something like that? Now, it's also important here is because the test equipment is rated for a specific voltage upper limit. Voltmeters are typically 500 to 1 kilovolt DC. Now they, of course, can go higher than that, but you need a special probe to do that. Scopes are typically 200 to 400 volts DC, but that tends to change based on the frequency of the signal. They have derating curves, which you can find in the manual for, depending on the frequency, how much voltage they can withstand. And then watt meters. I'm not sure why that is in there, but watt meters, not voltage, but watts. So be aware of the path to ground, and that's what happened to me. Make sure that you are not the path to ground. Keep one hand in your pocket while measuring an active circuit. Now that means keep the hand in the pocket and only use one hand here, if you go into the circuit and grab the case and then go in with your probe to measure something, that could be a bad day. Because that's what happened to me. And I ought to mention that the next day after that happened, my father came up and he took a meter, a voltmeter, not this particular one, but one very similar to this Simpson 260, which we'll talk about later. And he took the black and put it to the cold water, and took the red and put it to the light fixture, 120. So we ended up replacing that light. Now the next thing here is do not defeat the ground plug. In some cases, a lot of the newer homes, in fact all the ones that I have seen, they have the 3 plugs. And in a lot of cases, or it used to be that they didn't have that, but now every place has a three-pronged plug. Okay? So that's enough about safety. I just wanted to get that off my chest. So let's talk about Ohm meters. Now what we're going to talk about first is we're going to talk about a Ohm meter like this. This is a Simpson 260. It's a Series 6, so it is actually one of the newer models. It's not an original from the World War II era. And these are passive devices. They do not modify the signal. They don't amplify. All they do is really measure. They have a low input impedance that is not the same across the range. The measuring range is from 0 to 1,000 volts DC and AC. It takes a little skill to read, which we'll talk about here in a minute, and good for values that are changing. If the value is always the same, you know, a digital multimeter is great. But if you're trying to adjust something that is constantly changing, you're trying to peak that out, these are the best things for it. So we'll start out here. This is a 260, and it was the first compact all-purpose volt-ohm milliamp meter, and these are still made today in Wisconsin, by the way, made in America. So up here in this area is the meter. Now this has the mirror, which helps you read it, and it has the plug-ins here. You see, you have a C1 for there's one for 10 volts. There's a common and a plus. Over here it says 1,000 volts AC DC. Here's just a reading for 1 volt for really small measurements. And down here it says all terminals 1 kilovolt max, right down here at the bottom. So with this meter, you have to know what you're measuring. If you're going to measure AC volts, you pick this option on this knob, or negative DC, or plus DC, and it even has an off button. And I'll explain why that is important later. That's a really nice feature that they added to these with this Series 6. So you've got options here for 230 volts, 1,000 volts, 25, 10, 2.5, then you go into milliamperes. Then over here is your resistance ranges when you want to measure ohms. And there's 3 ranges for that. Now this little button knob right here, which turns, is the 0 ohms adjustment. And I'll talk about that when I show you how to set one of these up for a continuity test. So this is the big scale. This is the big scale. And this is what it looks like really zoomed in. Now this is a Series 8, not a Series 6. But so across the top here you have ohms. And then Here you have DC and AC. You have other ranges for 2.5 volts AC, and then you've got here's for AC amperage. So you use the same band for AC and DC right here. Now, if you were to go in here and set this up, let's say I want to measure a battery. So I would go in and I would set my range at 2.5 volts using the knob. What I would use is I would use this top DC scale here that goes from 0 to 250. But you divide that by 100, so this full scale reading here is 2.5. So it takes a little bit of knowledge to read this, and it should be coming in right about here for a 1.5 volt battery. So this is a little more. Of course, it's not auto ranging. You need to select what you're going to be measuring here. Here's 2.5 volts, here's 10. Make sure that you turn it on. Now here's the important point. Now make sure that you turn it off, or at a minimum, don't leave it on an ohms measuring scale, because this does have a battery in it. It's got a couple of them. If you leave that on resistance, then you'll run the battery down. And then you have to replace it. And actually on these meters, it's actually very easy to do, these newer ones. On the original ones, you had to take the whole back off. But on these newer ones, you just unscrew this big screw right here and the whole thing comes out. Then there's a battery compartment right there. Okay. Okay, so what I'm doing right here is I'm measuring a 1.5 AA battery. So I set the scale to 2.5 volts, and the meter is reading about 1.65. And that's typically for a fresh 1.5 volt dry cell. Now the way that this works is that this marker right here is 1.75. So this is 155. That's 160, 165, 170, and 175. So right around 116. That's the thing about these analog meters, is they're not absolutely accurate, but in a lot of cases you don't really need to be. So let's look at another battery. This is another one, testing a 1.5 volt. Meter shows 1.15. That one needs to be replaced. Because, and this is good because I'm so used to this. I have the meter setting up on a shelf and the leads hang down. If I need to test the battery, I just grab the leads, put it on there, and I don't hardly even need to look at it. I can look out of the corner of my eye and see what it is. I'm so used to it. So, now the resistance measure here, we'll set R times 1. And setting up for a continuity test, select R times 1 or any of the others actually you can use. Now you take the positive and negative, which is the red and black, and what that will do is the meter will swing all the way to the other side, which is 0 ohms. And then what you do is you come in and you adjust this knob right here so that it zeroes out. Now, it may eventually happen sometime that you can't zero it. It won't go that far. In that case, the battery's dead or on its way quickly, so it needs to be replaced. And this is useful for when you've just finished that new 10-foot power cable, 10 gauge, put the power poles on it, and you want to test it out. That's when you can use this. and it tests the continuity from one end to the other. And this is what it looks like when checking continuity and you get a good connection. You see it'll swing all the way over to 0. And it also works for RG8 and RGX. You know, the center lead to the center lead at each end, when you test that, it should swing all the way over, meaning a good connection. Same thing for the shield, but you should not have connectivity between the center pin and the shield. And that's how you would test that. Okay, any questions on VOMs? Okay, let's move on here. Hello.
Always leave it on the highest AC voltage on the older ones. This one will be off, like you're saying.
Oh yeah, right. Vacuum tube voltmeters. Now, can you tell I like analog yet? Yeah. I'm so used to it. It's what I grew up with. Okay, well, it'll measure everything that a voltmeter does. It is not passive. It will actually amplifies the signal, and they are very sensitive. I have one that sits on a shelf, and it will actually pick up, if I don't have the probe and the ground connected together, and I like switch on the microwave, it will pick that up. It will respond to that field. And this is the thing about the vacuum tube voltmeter, is that for DC measurement, it's got an 11 megohm input resistance. It makes no load on the circuit under test. And that is consistent across the range of measurement. And it's very sensitive because the voltage under measurement is fed directly into a triode, usually a 12AU7. Now, most of them that I have seen have 2 tubes in them. They have a twin triode, like I said, a 12AU7. Then they have another tube that's just a valve. And all it does is rectify the AC voltage that you're measuring. So in a nutshell, I'll show you here the circuit. And this is really, really basic. There's other stuff in there besides this. But this is it. This is our input over here. Here's our voltage dividers with our range switch. And as you can see, that input goes right into the grid on that triode. And this is the reference triode right here, because this is set up in a bridge. So when everything is in balance, no current will flow here, and the meter stays in one spot. It doesn't move. But when you apply something different to this one, they get unbalanced and current flows, and you get a reading. Now, here's one. This is WV98C. Yeah. Yeah, this is RCA, back when RCA actually made stuff. And yeah, and these are really good units. They have a couple, like I said, a couple tubes in them. They're AC powered, so you have to plug them into the wall. Over here is the range switch. Then they have a 0, which actually zeros the meter over here. And the way that you zero is you take the lead, the positive lead, or they call it an isolation lead. You take the isolation lead and hook that to the minus, the negative, the ground, and then you adjust your 0. Because like I said, it's very, very sensitive. It will pick up stuff out of the ether, you know, because it's so very sensitive. Now this center thing here is, I'll come back to that in a second. That's an interesting point for this particular one. Now here your ohm 0, we're talking about that on the Simpson, and then this tells you what you're actually measuring here, if you're measuring DC volts or ohms, and it also has an off button. Okay, so this portion right here is your input. Now that looks kind of strange. And it's like that because the guy who originally developed it, when he developed it, he wanted to use some shielded cable. So he got this idea, well, I'm going to use a microphone cable and I'm going to use a microphone connector. And that's exactly what he did. And this little black wire coming out here is the ground. And this just ends in an alligator clip that has a little rubber covering on it. I did not bring this one today, but this is, like I said, very sensitive. The cable is shielded, and we'll talk about the probe here in a second. Now you look at the scale, same kind of thing. Ohms is across the top, but it's reversed. So we'll talk about that. DC or RMS, that's AC RMS. Now this has a little scale here, and what it will do is it will show, I think my pointer's dying. No, it's still good. It measures peak to peak. So if you've got AC RMS, you can quickly look in here and you can see what the peak to peak voltage is on this little red scale right here. Then there's a low AC right here on the bottom. So this is a little closer look at it. This is in the ohms mode, because you see when it's open like that, like I said, it works reversed on ohms. So when you turn it all the way to ohms, the meter swings all the way over. And that's when you use your 0 ohms. So you see it right here. Now this is good because it shows you what you use the mirror for. This is what you use the mirror for, because if you look at this closely, you'll see the meter here, the actual pointer. Then behind it you see an image. That's the back of the pointer. So the idea is you take the actual mechanical pointer and line it up with the image in the mirror. And when you do that, then you are guaranteed of a correct reading. Then that's because as you look at it on an angle, it'll move around.
Parallax.
Yeah, parallax. As a matter of fact, that's what they call this mirror. They call it anti-parallax. So this is a little closer look at the controls. Right here you can see this is the connector for the lead. This is what the lead looks like at the business end. It has a little switch on it, and it's labeled DC and AC ohms. So when you switch that to DC, what it does is it puts in another 1 megohm resistor, and that's why they call this the isolation probe, because it just kicks in another megohm in it. This is the standard probe for the meter. There are other probes for it, mostly for amperage, for amps, and for high voltage. And the AC ohm selection is straight through. And remember what we said about knowing what you're measuring? Okay? It helps to know. All right. So that's the old stuff. Next up here, let's talk about the digital multimeter. This is the modern thing. I mean, it hasn't been around for that long. This is the Fluke 87. It's a modern version of the VTVM, high input impedance, mostly indestructible. To destroy one of these, you either have to be trying or having a really bad day. It has many additional features on it. It's got a peak hold, it's got a min and max hold, and you can see right here it's got different options. Right here is, and they got really nice international symbols too. AC volts, come on, AC volts right here, DC volts, they got millivolts, here's ohms. There is a diode for like continuity, and the milliohms will do that, and these are nice in the fact that when you get a good continuity, they beep, so you don't even have to look at them. And I would like to point out that the new Simpson 260 Series 8P, they beep too. Okay. Now I say mostly indestructible because a number of years ago I had a couple of friends who were working at a job site, and they were using one of these, and they wanted to measure an electrical panel, and the panel had been mislabeled. And I think the panel was actually supplying 2 kilovolts, and they put one of these across it. And to the meter's credit, it held it for 5 seconds. They were all right, you know. They recovered. They had sunburn from the arc flash, but other than that, they were okay. The meter didn't survive, but when you looked at the meter from the outside, it looked great. But when we took the cover off, and the inside was melted into a brick. So like I said, mostly indestructible. Now when you go out and buy one of these used, most of the time they're in terrible shape, because this is something that the electrician just throws in the back of the truck, because it's got this little rubber armor thing around it. It's tough. Okay, so currently available, it is auto ranging, so you don't need to worry about what the voltage range is. It will figure that out. High quality, tough with its other coating, and these aren't cheap. They are not cheap. They run about $300, and they make different versions of it, but they are really not cheap. But if you want a good DMM that'll last a long time, this is probably the one to get.
What's that model again?
87V. And there's other models, there's like a 115 and a 117.
George, that was $376 on Amazon.
Yeah.
With free shipping though.
Thank you. Thank you. But they're charging you. They're charging you $76 for the next day shipping, though.
Hey George, in the class, Paul and I emphasized on meters and radios, the smoke has to be in the radio. Once the smoke comes out, the radio and the meters do not work. So you gotta keep
Yeah, very true. And it's usually very expensive to put the smoke back in.
You can't get the smoke back in.
All right. So let's talk about component testers. First thing we're going to do is we're going to talk about LCR, which is inductance, capacitance, resistance. Then we're going to talk about tube testers. Something fun, believe me, you're going to love it. So let's talk about capacitance. Now the thing I'll say about capacitance is, and there's several of these out, if you go to Amazon, there are literally hundreds of these, page after page after page of these. Some of them tend to be very cheap, some of them tend to be expensive. What I would want you to do is one that measures ESR for capacitance. Now ESR is equivalent series resistance. And it is a qualitative measure of the capacitor. Now, sure, it has microfarads, picofarads, but that's a quantitative. ESR is qualitative. It tells you the quality of the capacitor. Lower ESR is better, and a bad electrolytic will have higher ESR. So that's why that is important. Now this next image, right here, testing a 45 microfarad capacitor, 47, excuse me, and it shows 49.32 microfarads, probably well within the limits. And the ESR is 1.6 ohm. I'd actually like to see that ESR a little lower on that one, but because that's a brand new one.
Did you say 1.6 ohm?
1.6 ohm. And this is what is displayed in the window. So what I'll do here is I have one of these here. So I'll put it in to the tester. And you'll see how this works. Yeah, come on. That didn't work. This is the problem with this. It's got one of these zero force insertion sockets to make it easy, but it makes it more difficult. So what you do, come on. So what you do here is you mount your test, you mount your inductor or your resistor or your capacitor in this little ZIF socket here and close it. Then you hit the blue button and it will figure out what component it is. Pretty amazing. So what I'll do here is I'll pass this around. That's the giveaway, by the way. I've got one here in a kit. So, and I was telling everybody before everybody showed up. And when I was at Xenia, I went to Joe Eisenberg's K0NEB, his kit building seminar. And he talked about one of these and said, "Oh, this company over here is selling these at, rock bottom price." So I went over and I bought two because they were cheap. Well, I only need one. So I'm giving one away. So that is the capacitor. Now, in this case, I'm doing a resistor. So all you do is put the resistor in there, and I do have a 1K ohm resistor, so if you want to see it work with that after the meeting, we can do that. You just put it in here, and I put in 3 little marks so you know which sockets are the good ones. And I'm measuring a 1K ohm resistor, and that's reading, I'd say pretty good, 99.7.7. That's only 2.3 ohms off. That's really good. Now,
How do you get the display to come back up?
you hit the blue button, press the blue button.
Okay, do you see the blue button? Got it, okay.
Yeah. And it does light up, as you can see. The camera didn't pick it up well, but now I didn't have an inductor, so I didn't do that one, but it works in much the same way. So that's component testers. Next up, yeah,
By the way, those are available for like $13 on eBay.
yeah.
It's like, I can't believe how cheap they are.
Yeah, and well, there are more expensive ones. There's, I know that Sencor, a company that's been around since dirt was new, and they make component testers, and they are very expensive, even the old ones.
I can't believe how well these things work for cost.
Right, very true, very true.
Might be worthwhile noting that they also work on diodes and transistors and a couple of other types of semiconductors.
Yeah,
Yes, they did.
So not just your simple components, pretty much anything you would want to solder together in a kit.
yeah. That particular one has got some traces on it and a opening and a hole over it. And so I'm not sure if that's for what that's for. If that's for like a transistor or a FET or something like that. It might work.
You put your transistor,
Yeah, service mount.
you put your transistor on pins 1, 2, and And it will tell you what kind of transistor it is, what the beta of the transistor
Wow.
is, whether it's PNP, NPN, and also the pin assignment for each 3 of those pins.
Yep.
So, you know, there's a difference between a 2N222 and a PN222 as far as the pin layout, and you can never make a mistake if you use that meter first.
Yep. Okay, so tube testers. And these measure emission and something called dynamic mutual conductance. And they are easy to use. So, if you want to test tubes, you have to go get one of these. Okay. Okay. All right. Well, now, what did I say? Oh, remember these? Okay, seen in most drugstores in the 60s and 70s. You go into a Rexall or a Super X, there's this hulking thing. You know, radios, you reach in, you pull out the tubes, okay, not too bad. But a TV set, wow, you're going to reach in there. And yeah, keep one hand in your pocket is very true. And what's really funny is that while, like I said, we were repairing TVs, I can only remember a couple of cases where a tube was the problem. Usually it was a capacitor that disintegrated into 2 or 3 pieces. I did see one tube blow up, explode, but other than that, very, very sturdy. But they do go soft, I guess, if that's a technical term. And we'll talk about that later. But anyway, I just would throw that in. That was kind of funny, I thought. So, we'll look at a tube tester here. And I have one of these. This is a Seco 107A. You don't see the A models, you see just the straight models that don't have a letter. And here is the warranty card that was never filled out. Minneapolis, Minnesota, and it doesn't have a zip code, so that's old. Okay, so this is essentially what the thing looks like. Yeah, sure. Yeah, the top cap cable is buried underneath the AC. Here. Yep. So this is what it looks like. I'm not going to pass this around. But these sockets over here are presets for various tubes. And this is what you use for if you've got a tube that you don't have over here. So I'll put that over here. You can come up and take a look at that. So
What would you guess the vintage is on that?
I think it's 62. Because they came out with the B, which looks different. The B and the C are flat instead of having this angled surface, and they're just flat. And the knobs are a little different. Now the 107 is different in that it's got another set of sockets on a box that comes out on a cable. So yeah, this is the 107A. It's early 60s, I think. It does the emission testing and dynamic mutual conductance. Now to go through the controls here, got a fuse here, very nice. Got sockets right here for various tubes. Here's the on-off switch. And what this also does is it adjusts this little eye over here. You've got a tube that looks like an electric eye, and they put a little eyebrow on it. And what that will do is it will sit there and open and close depending on what condition the tube is in. Here is the DMC meter. It shows bad or good. Here is a special type switch. Use the red button to adjust the line to center. This is filament volts. This is to adjust the center line. This is the load. This is how you test it right here. And then this right here, this bottom part is how you set up the pins, or I believe that's how you set them up. I just go by what the manual says. I never really looked into one of these to see what all of this is. So this is the book that comes with it. And they have updated version of this out on the internet. But it's got all the tubes in it. And there's also another sheet which is like an addendum that has other tubes that that came out after this one. So first thing we do is we find the information for the tube to test in the supplied booklet. Now what we're going to be doing here is we're going to be testing a 6AZ8, which is used as an IF amplifier in a Heathkit SB110A. And that information is right down here. So what we do is we come into the book, we get the information. You can see the type here is 6AZ8. These are filament voltage. This is the F and F1. This is the Q. This is the load, and this is the special. So first thing you do is you set the filament voltage to 6. Now first of all, and I probably had it on the other slide, is don't put the tube in there yet until you get everything set up. Because if you've just been testing a 12AU7 and your filament voltage is set to 12 and you put the 6-volt tube in there, that probably wouldn't hurt it. Because they are really tough, believe me. So anyway, we set the filament voltage to 6, and we're using the switches. We set 4 here to the F1, the 5 to the F2, and the 6 to the Q. Then we set the load to 60. Then we set the special type to A. Okay, so you plug the tube in and you let it warm up a little bit, because it's a tube. It's got to warm up. It's got a little heater inside of it. And I swear that you could see that thing glow, but with the flash and the shutter speed, you probably can't see it. It's not glowing. So you let it warm up, and what will happen is if the tube is, quote, gassy, then what will happen is this eye will slowly start to spread open. And if that happens, then that's a bad tube. That's really suspect. Now what gassy means, nobody's been able to really explain that to me. I think what it means is that the air is getting into the tube, because when they manufactured these, they didn't pull a complete vacuum on them. I mean, this is a production environment. You can't pull a complete vacuum on these in the time it takes to manufacture one of these. So what they would do is they would use something called getter, which is something that they would boil off an element inside the tube onto the side, and the getter would absorb the rest of the oxygen in the tube. And if the getter starts to release that back into the tube, then it goes gassy. At least that's what I think it is. Does anybody know?
I think you're
I
right.
think you're right.
Yeah, you're right.
You're right? Okay.
I used to work for Tunstall. I saw them make vacuum tubes.
Oh, yeah.
Basically what they did was pull a hard vacuum on it, seal the glass, then they ran it through an RF induction furnace that heated up the getter. They call it flashing the getter, and that
Yeah.
would gather up any last little bits
Yeah.
of gas that were in the tube.
Okay, so I wasn't wrong. Great.
Operation in a way.
Yeah.
If it's leaking, if it leaks the vacuum and you get water absorb the oxygen and it turns white. So
Yeah,
you see-
what they had to do was use RF heating to heat up the plate of the tube to try to drive any gas that was stuck on the surface of
Yeah.
the plate or any of the elements inside
Okay.
to break that loose, so that then the getter would get it.
Yeah.
And what'll happen sometimes if you get a gassy tube, that getter looks silver, it'll turn white. And if you see that, don't even bother testing.
Yeah. And it appears like a little mirror on the side of the tube. Yeah. Okay, with all that done, what you do is you hit the switch. There's this little, it's a lever, it's a momentary, and you push it forward, and it tests it. And you do that, and it swings over into the good. Yay, good tube. But, wait a minute. What did we really test here? And let's think about this. This is an IF amplifier tube. Did we test it in that capability as an IF amplifier? Nope. So that's why they always say the best place to test a tube is in the circuit that was designed for it. When in doubt, swap it out. That's why it's always good to have some spares around. So I forgot to ask the question, who in here has ham radio tube equipment that they use on at least once in a while? Excellent. 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 I have a SB102 and an SB110A Heath kit that I use once in a while.
Do you tap the tubes for microphonics?
Yes. Yeah, that is something that I did not mention. I should have put that in my notes. When this tube is up here and lighting and warming up, it's good to have a pencil, a wooden pencil. You don't want to use anything too hard. Just use a wooden pencil and sit there and just lightly tap the tube. And watch this eye here and see what it does, because sometimes it'll sit there and it'll jump. And that's like what you were saying, microphonics, if there's something loose in the tube. Okay.
Basic tube test is just checking the gain of the tube.
Yeah.
But known voltage put into what you're supposed to get out.
Yeah. It's testing that dynamic mutual conductance, which is like the number for the tube. And you know, if you look at like a 6L6, which is real popular with guitar people for their tube amps, you know, like KT88s and stuff like that. And those are still made today.
Mostly in Russia.
Mostly in Russia, and I just learned the other day that Germany is making 6L6s. Yeah, very expensive, as you would probably.
I still have my old supply.
Right. So, yeah, still around. But again, I mean, if you put a 6L6 in here, which is a beam power tube, and test it here, you haven't verified its operation as a power amplifier. You just tested the dynamic mutual conductance. That's all you've really done. Now, if it fails the dynamic mutual conductance, I can tell you it's not going to make a good amplifier tube, but. Okay. So now we're ready for the big one. Oscilloscopes. And I don't intend you to be an expert on this by the end of this by any means. I don't expect you to have your cap and gown ready to graduate, but I just want to show you some of the general features that you see in them and talk about them a little bit. So a scope gives you a quantitative and a qualitative measure. Now quantitative, you're looking for a number. You're looking for a number. Maybe you're looking for a frequency. Maybe you're looking for a peak-to-peak voltage. Qualitative, because you get a sense of what the waveform actually looks like, because you're looking at it as it changes over time. So if you hear a tone in your ear out of, say, an amplifier, and it sounds very pure, well, you can run it through a scope and you can see, no, that's not a good signal at all. So let's take a look at a scope. Oh my God. Wow. Okay. So we got several things to talk about, and I'm not going to describe everything here on the screen, believe me. We're just going to talk about a few basic things that are present on all scopes. Now what this is, it's a Tektronix 2252. It's a 100 megahertz scope. It is a transition scope. It was made from the early 90s to the mid 90s. And like I said, it is a transition scope. It's still analog, but it does have digital capability. Matter of fact, this scope is very unusual in the fact that it will print the trace to a printer, a dot matrix printer, which, as you will know, are really available nowadays. And have you seen the prices on dot matrix printers, by the way? 300. You know, I can buy an inkjet for 25. Okay. So this is 100 megahertz bandwidth, and we'll get the bandwidth in a second. First of all, let's kind of go through the controls on this thing. Now in scopes, you typically see these controls at the very bottom under the screen. There's the power switch, that's an easy one. Now this scope is kind of special. It's got an A intensity and a B intensity. The A intensity is for the trace overall. Now this is a 4-trace scope, and I'll talk about that in a second. But the A intensity is generally for the traces. The B intensity is for special trigger modes. You can amplify or intensify certain sections of it. Now the focus, obviously you want a nice sharp trace, so that's what that is. This little hole right here is trace rotation. So if the gun on the neck of the tube gets loose or whatever, and you need to adjust the tilt of the scope, that will do that. Readout measures the little numbers that will appear on the scope that show voltage per division and seconds per division. Then you've got scale illumination, because these have a scale built into them. Let's kind of move back, take a look at this again. Okay, here's a better one. Now you see these numbers right here. Here's 0.5 volts. So what that is doing is that is showing the readout, and you can vary that. If you want to turn it off, you find it distracting, you can turn it all the way down. Scale illumination is it will light up the scale here, this reticule or gradicle, whatever they want to call it, here on this particular scope. And it's got lights on the edge of the scope. So when you turn that up, it lights up the edges, and these become more prominent. So that's what scale illumination does. Now, we'll look here at, this is a volts per division. This is the y-axis. This is up and down, so we're measuring volts. So these controls here are position. It will move the trace up and down. The mode selects what you want to see. Here you can do channel 1 or channel 2, 3 or 4, or you can add the traces. You can add channel 1 and channel 2 together to get a different item. And then here you have an interesting button called Chop or Alt. And what that will do is, Alt, what it will do is it will alternate the trace. It will draw A, then B, draw A, then B. On Chop, what it will do is it draws a little piece of A, then it does a little piece of B. So that's what it's doing there. Volts per division, like I said, that's what the divisions are. So you can adjust that, and it is usually got stops, so as you turn it, it'll go chunk, 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 chunk like that. In the center here is a control called var, which is variable. And when you do that, it goes outside of that particular setting. And as you can see right here, it's showing the little light here is on, telling you that you've turned that var on, so you're no longer in a range.
You're out of calibration.
Yeah, out of calibration. Now you've got a couple of items here called coupling, AC and DC. And that's very important, but you've also got a ground coupling here. So I first want to talk about the ground. What the ground does is it grounds the input internally. Now it doesn't ground this, it grounds it internally. And what that allows you to do, if you're doing a quantitative measure, what it allows you to do, it allows you to take that trace and center it on one of the lines, so that as you get a reading, you'll be able to actually measure it. So that is what ground does. Now, AC and DC coupling. Now we saw over on voltmeters, you had to tell it what you wanted to measure, AC or DC, okay? That's not what you're doing here. Don't think AC and DC with these, please. What you're doing is you're specifying how it's coupled internally. For DC, that means direct coupling. So if you've got a signal that's got a DC offset on it, and you want to measure the DC offset, what that does is direct coupling. It's straight through. AC, think of AC as active coupling, not alternating current. Because to the scope, AC and DC, it doesn't mean anything. It's just displaying something over time. So what AC does is it puts a little capacitor on that input, which removes your DC offset. So if you want to see a signal without the DC offset. Okay, and that's very important, because don't think that you can do something like, well, I got a new scope. I'm going to go see what my 60 hertz on my outlet looks like. And you go in there and you plug it into the wall, and then when the fire trucks leave, you figure out what you did wrong. Okay, don't do that.
Can you do that with an attenuator on it?
No. You could probably do it because, well, they do make high voltage probes for these. I mean, this one's set, I think 400 volts. They do make high voltage probes for them. The problem is isolation on these, because this connector right here is connected to the ground plug that you plug into the wall. So if you go in there and plug it into the wall, because there's a neutral and a hot, and if you get it wrong, poof. Yeah. Now, if you had some sort of isolation transformer between the scope and the wall outlet, you could probably do this very safely.
I found it out the other day. I was measuring voltage on with a automotive scope that I have. I was measuring Arduino voltage, and accidentally pulled my ground off my DC power supply.
Mhm.
It stayed running.
Okay. Okay, so this is seconds per division. Now this is the x-axis. This is where it's changing over time. You see 20 nanoseconds here, 0.5 seconds. And of course it's got the variable and the uncal right here. So as you change that, that's what changes the time scale on the x-axis of the scope. The last thing I want to look at here is a little switch, and you do find these on almost all scopes, is the thing called beam find. Now when you're looking at the scope and you know you've got a signal coming in, you can't see it. Where is it? So you hit beam find, and what it will do is it will take the trace, the whole thing, and squeeze it down into like a 1x2 area on the scope. So you can say, oh, the trace is over here. So that allows you to find it. Now, this little terminal right here, labeled probe adjust, and I am so happy that they call this probe adjust, because on a lot of scopes, it doesn't say that, it says calibration. Don't believe that you can calibrate a scope with a 1 kilohertz, a 0.5 volt, 1 kilohertz sine wave. But what it does do is it helps you adjust the probe, and it is a very good signal, so you can use it for other things as well. So what you would do is you'd use the probe adjust to calibrate or compensate for your 10x probe. Now, the next thing let's talk about probes for oscilloscopes. Special subject, because it's kind of like our senior volt ohms. It's a shielded cable. It's kind of special. Expensive, yeah, very expensive, particularly in the higher bandwidth, like 400, 450 megahertz. Now that's an expensive cable. It's one of the most important part of the scopes, and the probe should have the same or better than the bandwidth of the scope. So you go out, and I'm not saying do this because you don't need to do it. Go out and buy a 400 megahertz bandwidth scope, and then you buy a cheap probe for 100 megahertz. Well, you're wasting your money on your 400 megahertz scope because it won't read properly. So nowadays, when you go out and you get probes, this is basically what you get. And I'm not knocking these probes. These are actually very good. This is a probe. It's a 1x and a 2x. It's got a little switch here on the side. You can switch it to 1 or 2x. This little black lead here is the shield. It's the ground. And it does come off. And what's interesting about these probes is you pull the thing back here and there's a hook which lets you attach it to something. Well, in the days of surface mount, it's really not helpful, is it? So what you can also do is you just take it here by this little ring, push up like that, and then you get a nice sharp point, and you can use that. So I'll pass that around, take a look at that. That's kind of like the generic probe that you get nowadays. All right, now this is not a generic probe. This is the Tektronix, the real thing. If you look at this and you look at that, hey, there's not a lot of difference, to be quite honest with you. The one difference that you have is this little pin right here that's spring-loaded. And that's called the Readout Pin. So if you're looking at scopes, probes on eBay or a testing site, and they say Tektronix probe with readout, that's what they're talking about. And what that is for is that when you put it on the scope, this little readout pin will tell a scope, oh, this is a 10x probe, and it will automatically adjust your reading at the bottom of the scope. So you won't have to think, oh, I got to divide by 10 because it's a 10x. The scope does that for you. Okay, I'll pass that one around. Not a lot of difference between the two in reality. I got that probe new in the wrapper, NOS. So there's two types of probes. The 1x type doesn't do any modification to the signal. So what you see is what you get. The 10x probe reduces the signal amplitude by 10 times. So 10x is not 10 times, 10x is divide by 10. And that's useful if you're measuring something in high voltage. Your scope is only capable of doing 200 volts. well, then you can measure like a 600 volt signal. Now the 10x probe has to be calibrated due to the circuitry inside of it for a correct measurement. And that's when you use your little calibration tab. And when you do that and you put it on the scope, what you'll get is you'll get a trace. It's square wave. And we've got several versions here. So the one on top is correct. You want that. You don't want the other two, overcompensated or undercompensated.
Flat top, flat bottom.
Yeah, right. Flat top and flat bottom. And when you compensate to them, if you look on the little scope, I think the cheap one, the compensator is on the little block, and on the Tektronix probe, it's actually on the input. And you ought to use non-conductive, meaning plastic, like this one right here that came with the Tektronix, and you can use this for anything that you need. Because if you go in there with a piece of metal, it will affect your compensation. Okay. So that is scopes. Any questions? Yep.
Yeah, one thing, I deal with really high voltage, three-phase electrical circuits all the time.
Yep.
And one thing I use the Greenlee meters, those are all excellent. But
Mhm.
the Fluke has the probes that are the insulated ones that you can control how much of the exposure of the conductor on the end
Okay.
is going in those circuits, and that's something maybe you may want to comment on or mention to them.
Yeah.
Prevent shorting out or having arcing on, the safety stack, because a lot of times people don't think about the ramification of an arc flash if they even
Oh,
know
yeah.
what it is.
Yeah. Yeah. So for scopes, before we get into spectrum analyzers, if you want to go out and buy one, you can certainly do that. I have a problem. I love Tektronix, so I bought a Tektronix scope. If you don't have that affliction, then you can go buy a different scope. Leader, a company that makes scopes, is still, I think they're still around, they may be. They make some great scopes. And as far as bandwidth, the old saying is, how much bandwidth do I need? Well, as much as you can afford. Well, that's not really the case because high bandwidth scopes are very expensive. I know that Tektronix recently just bought out some new scopes, $12,000. And even the ones that are made by Siglent and Rigol, their high bandwidth scopes are even very expensive. So a leader, for what you're doing for ham radio, you probably really only need 50 megahertz. Because if you remember bandwidth, you look at bandwidth the same way you do for like a filter. It's the 3 dB point, it's half power. So if you're just looking to look at a signal and get a qualitative measure, then you can measure a 100 megahertz signal on a 50 megahertz scope. You still see a signal, but the value won't be right. So yeah, leader, B&K Precision, any of those scopes are great. Don't be wooed by high bandwidth, and don't be wooed by the number of traces or the number of inputs, because you say 4 input scope, wow, I can have 4 independent traces. Well, no, you can't, because usually the first and second are the actual inputs. The third and fourth are usually used for digital or triggering signals. So they kind of like say 4 input scope. Well, it's actually 2, but you use the 3 and 4 for special items. Okay, so we come to the end here. Quantitative and qualitative measurement, once again. Now this signal is different. You're not looking at it in the time domain. You're looking at this in the frequency domain, which is something that you really don't typically think about. Now, I have to admit, I do not have one of these, but I have something else, which kind of leads into our discussion about solutions from the PC world. How many of you here listen to Ham Radio Workbench podcast? Two guys. Okay.
Never heard of it, so what is it?
It's the Ham Radio Workbench podcast, and it's a podcast run by a couple of guys. One of them works for National Instruments. And if you want a down and dirty, technical ham radio podcast, they're the ones to get into, because they will get technical on you. So they introduced me to a product called Waveforms. There's a company called Digilant, and they're run by National Instruments. And let me tell you, they're doing some amazing things. And I urge you, if you are a technical person and you want to learn about SDR, and I just don't mean about using an SDR radio, you want to learn about SDR to the point of where you want to write your own radio in code, you need to take a look at their site. So, Digilant, D-I-G-I-L-E-N-T. I was reading, while I was preparing for this, I got caught up in a blog post that somebody had done. National Instruments has an FPGA programming kit, a tutorial. Now, FPGA is field programmable gate arrays, and it's what you use to write, well, I say write, it's what you use to build an SDR radio. You actually write code, I guess you could call it code, and then you put it into the field programmable gate array, and that's what implements your fast Fourier transform, and that's what gives you your filtering capability. But that's way beyond the scope of this course, believe me. I wouldn't be the right guy to teach it anyway. So I'll show you here. This is something that's part of the Diligent Analog Discovery 2, which is something that they are selling. And if you get on their site, go to Ham Radio Workbench, you can get a discount on this little device. I have it right here. And it's powered by USB. And this is it right here. That's it right there. Now what's in here? Voltmeter, scope, frequency counter, frequency generator, spectrum analyzer, logic analyzer. And here are the leads that come off of it. They also sell an attachment. You can attach scope probes. Gives you BNC connectivity. And it's all USB. And I have my laptop back there. If you want to, maybe after the presentation, I can hook it up and we can play with it. So this is the frequency generator. And what it's doing is it's just doing a sine wave. It's set to 1 kilohertz. So I bring up the spectrum analyzer in waveforms. This is what you get. Now that's exactly what you would expect, is that at 1 kilohertz here, right here, you got a big spike, which is what you're sending. Now all this other stuff is crud, and that's why I can't get a good noise floor where I live, is probably because of this right here, because it's picking that up out of the air. But there's a spike for that 1 kilohertz sine wave. So let's try something. Let's do something and let's input a square wave. What do we get when we do a square wave? This. This is exactly what you would expect for a square wave, because you've got, right here, you've got the big harmonic at 1 kilohertz. Then every odd harmonic, you have a spike. So a square wave is actually a summation of sine waves. And I wish that when I was learning this back in school, when I was in discrete and continuous systems, I would have been able to have something like this. because you can see the math works. Look at the math. Math works great. But to see it like this, really amazing. Really amazing. And this just shows what kind of processing power that they're doing. Because if you look at the way the science has progressed, the Fourier transform was created, you know, what, at the turn of the 18th and 19th century. The fast Fourier transform was theorized in, I think, the late 1890s. But it really wasn't until the 1960s that we had computers that could actually do that. And now we can have this sitting on our desk in a laptop. Pretty amazing. Okay. So extra reading, or exercises left for the viewer. Now, if you're interested in this stuff, you want to learn more about it, you're interested in fixing old equipment, or you just want to immerse yourself into electronics, then here is a bunch of guys that will do it. First up here is W0GRW. These are all on, most of these are on YouTube. First thing here is W0GRW. You can just go into YouTube, type him in. His name's Alan Wilkie. And I first started watching this guy a couple of years ago, and I'm like, who is this guy? Where does he get this information? Okay, he works for Textronics. All right. So he knows this stuff. He thinks this stuff is what he says, because he was saying he did a seminar for a radio club on scopes. That's all I talked about for an hour was scopes. And he said, you know, I look at these circuits the way a scope does. So that's why he knows this stuff inside and out. Now, EEV Blog is a gentleman. I think he's in Australia. He is a testing equipment nut. He will go out and buy just loads of the stuff. I mean, truckloads, and sort through it, and I guess he resells it. Mr. Carlson's lab got a lot of testing equipment. He also fixes a lot of stuff. So does TRX Bench, and it's interesting to see these two guys, the way they think through something. If, you know, if a radio won't transmit, or it won't receive, or it won't turn on, you know, what do you look at first? What do you do to figure that out? Now, TechWiki. If you've got my affliction, you love Tektronix scopes and equipment, go to TechWiki, and they have every single scope or piece of test equipment that Tektronix ever made. And in some cases, they have the manuals in PDF form, because Tektronix and other companies like Hewlett-Packard even have a very liberal position on equipment that is no longer in production. They basically put the books in public domain, so you can go out and print them out. And then there is a very active group on groups.io called TechScopes, and I think I get a delivery from them about 5 times a day, because they talk about them constantly, about how to fix them. So I got manuals here. I got the operator's manual to the 2252, which is the one I have. Actually, the thing is that about this much of the manual is operation. The rest is specifications. Yeah. Here is the 2252 Portable Oscilloscope Programmer Manual. Programmer manual on a scope? Yes. This has a thing on it called GPIB, IEEE 488, so you can actually talk to the scope on a computer. And then I have here, I do not have the service manual for the 2252. I have the service manual for a 2445, which is a much more advanced scope, okay? That's the service manual. And it's got circuit diagrams like you would not believe. I would never think that a piece of equipment would have so many different power supplies. There's a 48 volt supply, a 17 volt supply, a 12 volt supply. And this is something that I recommend that you do. If you want to go out and buy a used scope or even a new scope, go get the user manual first and to read through it and make sure that it'll do what you want and that you can understand it. For if it's an old scope, these are good, and that Tech Wiki is good too. It's good to know how to trigger the self-diagnostics. Because you're looking at the scope, you plug it in, it says good. Well, let me see if it's in calibration. So you run through the test routines. Now it's not in calibration, so now you've got to get it calibrated so that it works right. That's it. I got a black screen. So, any questions? No?
Back there.
Oh, I'm sorry.
Well, you sort of answered it with the self-diagnostics, but I picked up a scope a couple years ago.
Yeah.
At Goodwill or something random. What would be a good way to find out if it's broken, or what are the common things to be bad on an old scope like that?
Well, it would depend upon the scope.
I don't remember model numbers.
Yeah, right. I mean, these scopes, these transition scopes, were kind of like what was happening to ham radio at that time. You know, they had a radio and they kind of put a computer on top of it. That's what happened here. Same thing with the ham radio. They had a radio and they put a computer on top of it. Now they take a computer and turn that into the radio. And it's the same thing with scopes nowadays.